We're gonna start calculating this two-way slab using the Eurocode by the British Standards. This two-way slab will have these conditions for supports around there. In this side it will be discontinuous. What it means it's free. We could say it's free. And this side will be continuous supports, and this side will be continuous, and this side will be continuous. So this reinforced concrete slab will have in the minor side 5 meters and in the major side 7 meters. The total depth will be 0.70. Since I like to use this little rule, span divided by 25 or 35, I'll go by 30 in the middle. So the minor span is 5 meters divided by 30, what gives us 0.167. So we can say 0.17. The effective depth, I will just speed this calculation and subtract 3 cm. Usually I use this form for calculation. So I'll subtract this cm from 17, what gives us 0.14 meters. The type of concrete will be the C20-25, so the FCK 20 megapascal. The FCD I divided by a safety factor of 1.5, so 20 divided by 1.5. The FYK for steel, I use the S400, so it means it's 400 megapascal. For the FYD of Cálculo, I divided by a safety factor of 1.15. The lever arm will be calculated later. So as loads we have the self-weight, that is the total depth 0.17 multiplied by the density of the reinforced concrete, that I consider 25, which gives 4.25. For floor finish we use 1.5 kilonewton per square meter. For partition wall, let's consider 1.5, and a live load of 4, since I'm considering it's a shop of commerce where the slab will be. So it's a two-way slab by a motive, very clear. It's supported, as we can see, it's supported in 3 sides. So, and because the major side divided by the minor side give us less than 2, it's 1.4, so it's a two-way slab. We have to check for calculate this reinforcement of this two-way slab. We need to check the flexure, the bending moment, and the shear. So we will use a method in the British Standards BS8110, table 3.14, bending moment coefficients for rectangular panels supported on 4 sides. So we have these coefficients that we'll use to determine the moments on the slab. And as we can see, the type of panel will be interior panels, or it means it's supported in 4 sides, or one short edged container or one long edged container, and so on. And then this is divided, this coefficient, by the negative moment, that will be these ones, and in the positive moments that will be these ones, and this is still divided by here will be values for the shorter span and here for the longer span. So this is for the bending moment, and we have a table too for the shear, where we call it BV, and here BS. We can give it other names. So returning here, so since we have all these types, we have these options. Let's see, one major side continuous, that is on that British Standard table. One major side continuous. No, what we have is one major side discontinuous. The next one, two adjacent sides discontinuous. No, we don't have two adjacent sides discontinuous. Two major sides continuous. No. Two minor sides continuous. No. Four sides continuous. No. Four sides continuous. No. One major side continuous. Yes, this is the type of coefficients that we'll be looking in the British table. So let's start by checking the bending moments. First, let's factor the loads. So it will be 135 the permanent load plus 1.5 multiplied by the variable loads, and this is 135 multiplied by the self-wave plus the 4 of lineage plus 1.5 of partition load that we are considering. All this plus the variable loads that will be 1.5 multiplied by 4 that we are considering slide load. This is in the Eurocode, the factoring. So we can represent this slab this way. So this side is continuous, this side is continuous, here continuous, and here discontinuous. What it means is that here in the discontinuous side we can have another slab here. To calculate that later in another video, I'll explain how to balance the moments from the side of slab with the side of slab to get the right moment to calculate the reinforcement. And here too can have in this side of the slab another slab, or it can be a concrete wall, a reinforced concrete wall that will give some rigidity. So given this rigidity, then you have moments. Here in the discontinuous side, this is why we even going to consider zero the moment on that side. So continuing the bending moment. So for the shorter side of this slab will be, for example, in the shorter side we'll have, in this side we'll have a positive bending moment here on the middle span. It will be equal to this M1 here. M2 will be a negative because it's in the corners. M2 will be perpendicular to the shorter side. M3 will be on this side, perpendicular to the shorter side. So that's the coefficients we are looking for, then the coefficients of the shorter side, because these moments, this as you can see, this is a double arrow, so it's like torsion. So the moment will be transferred to here on the shorter side. So that's why we're going to find the coefficients that are perpendicular to the shorter side. Then we have so we have M1, M2, moment 2, M3, and then we have in the longer span M4, M5, and M6 on the slab that will be perpendicular to the longer side of the slab. So, okay. For M1, it's in the middle span. It will be on the shorter side. We have to find the British table. So one long edge discontinuous. It's the type of slab we have. And it will be positive M1 at middle span. So it will be these values, and it's perpendicular to the shorter side. So the shorter side is beta to what we are after will be, and the major span divided by the minor span is 1.4. So it will be here 0.051. So the equation will be always beta multiplied by the factor load multiplied by L, the minor span elevated by 2. Always this, it will be always on this for the moment the minor span on the shortest side and on the longer span. So here we have a 0.051 from the table for beta. The factory load, we know, we calculate it's 1579. The minor span will be, so this side, the shortest side is 5 meters. So 5 elevated to 2. So this will give at this moment 20.13 kilometers per meter. We place it there in the middle span, M1. So M2 will be on the corners of the shorter side. It's perpendicular to M2. It's perpendicular to the short side here. And since it is on the side of discontinuous, so here we can consider the moment 0. That's why we need to go check these values there. M3 will be here on the side of continuous on this corner, perpendicular to the shorter side. So, and it's on the corner, so it will be a negative moment. Let's go to the table. One long edge, negative moment. The shorter side 0.068. 0.068 multiplied by the factor load, multiplied by the minor span elevated by 2, that gives us 26.84. Okay, we place it there. Then we have for the shorter side all the moments. Now for the longer span on this slab, we have M4, M5 and M6. So for M4 it's a middle span related to the longer side. It will be positive moment, so we go to the table. Positive moment at middle span 1.4. So at these coefficients are for the shorter side, for the longer span is in this, so it will be 0.028. 0.028. The factor load we know it's 1579. The minor span continues being the minor span always in this type of formulation. It's 5 elevated by 2, what gives us 11.05 middle span of the longer span. 11.05. So M5 now on this side of this corner. So M5 will be beta multiplied by the factor load multiplied by the minor side elevated by 2. So it will be on the corner, so it's a negative moment. on the longer span, we go to the table, negative, longer span, longer span 0.037, 0.037, multiply by this, multiply by the short span divided by 2, give us 4061, 1461, M6. It's a negative moment on the corner, and it's a continuous side, so it will be exactly the same. The coefficient 0.037 would give us 14.61 like in the other side. These two are the same value in this case. So continuous by the British code, okay, they like to use this K, normalized bending resistance, that is the FCK, instead of using the safety factor already here on the concrete. No. So they use this K, is the factor in moment divided by B, multiplied by D, divided by 2, multiplied by FCK. And we'll need later to calculate this lever arm in single reinforced concrete by the Eurocode. You calculated the Z, the lever arm, by this equation. It has to be equal to this, and has to be minor than 0.95 multiplied by D, the effective depth. So this value has to be always limited by this one, 0.95 of effective depth. And the main reinforcement will be calculated by this expression, the factor in moment divided by 0.87 multiplied by FYK multiplied by the Z, the lever arm. So the FYK, it's exactly like the same other expression. This FYK is already with the safety factor. If you see 1 divided by, so this is the steel, so it gives you here, getting, okay, here it's already with a safety factor 0.87, so this FYK is already with 1.15. This is why this expression shows like this in the British code. Okay. And to calculate this reinforcement, we'll have this always to check this minimal, the minimum reinforcement that is given by 0.26 multiplied by FCTM multiplied by B multiplied by D divided by FYK, and this will always have to be minor than this one, 0.0013 multiplied by B multiplied by D. So this minimum reinforcement, the reinforcement that will have, it has to be the maximum between these two values. And the main, this reinforcement, we can call it main, it has always to be minor than the maximum reinforcement that will be given by this expression, 0.04 multiplied by the area of the concrete section, the cross section area of the concrete. So this is why I have this expression here. So the reinforcement will be between these values. They are being limited by these values. So on the let's start by the shorter span. Shorter span, as we see here, will have this condition. On this side there will be rigidity. This is why I put it like this, and it has 5 meters. So, and here the slab, it's simply supported, and she can easily go up or down, and this is why we consider here on this corner moment 0. On this other corner negative moment will be, and here on the bottom we consider a positive moment. So starting by the minor span, on the bottom we calculated it will be in middle span of this one. On the bottom will be, so this one M1 perpendicular to here will be 20.13 factor moment, and the K that we calculated will be given by this expression. This is the factor moment divided by B, that is 1 meter, multiplied by D, that is 0.14, multiplied by F elevated by 2, multiplied by FCK, that is 20. It gives us, of course, this on the same units that we convert. So this is why I put it here, 10 elevated by 10, 3. Okay, so this K will give us 0.051, and it has to be, we have this condition on the code that has to be, this one has to be minor than this one, 0.167, that is limiting this K. So when this happens, it's single reinforced, otherwise it will be double reinforced. And this K is minor than the K limit, that is 0.167, so singly reinforced. The lever arm, so for the lever arm on this expression that we use, it will be always Z. We have this K, we use this K on that expression, and we get the Z from this expression. Will give us 0.133. So, for main reinforcement using this equation, so we'll get 4.35 square centimeters per meter. So we transform it for centimeter, here expression. Okay, we get 4.35 square centimeters per meter. So for the, here on the bottom, 20.13 kilonewtons for a moment. The reinforcement that we'll need, it will be this one, 4.35. We check the minimum reinforcement is given by this equation. If we check it, so the minimum reinforcement, it's the 0.26 multiplied by FCTM. The FCTM is on the Eurocode, on tables for this concrete. So if you go there, FCTM, C2025, give us 2.2. 2.2. So here the minimum reinforcement multiplied by P, that it will be 1 meter, multiplied by D, that it will be 0. The effective depth, it will be 0.14. And I make this multiplication, so I transform everything to the same units, divided by FYK, that is the FYK 400 for steel, the type of rebars, the iron rods, and we check the maximum too from the other expression, 0.0, to see the minimum that we're going to use. We check the 0.030 multiplied by B, that is 1, multiplied by D. course in same units. And the maximum between these two will be 2.002 square centimeters per meter for reinforcement, minimum reinforcement. And for spacing, I like to limit it to 25. Of course, you could go to 400 millimeters and to 35 millimeters. I like to limit this to 25 or 1.5 of the total height, total depth. So 1.5 total depth here is 0.17, what gives 0.22. 17, 0.255. So I like to limit to 25. I put it here for spacing. So starting here using the spacing of 25 and iron rods of 8 give us this value. That is already enough for the minimum steel. If you put it more, it will be much more bigger, and here it was really on the mark, 2.01 square centimeters per meter for minimum steel. So here what we are seeing in the middle span on the shorter side, 4.35. So it's check the minimum, 4.25. I use the space of 25, rebars of 12. I didn't use 10 because if I put 10 it gives 3.14, that is smaller than 4.35 that we calculated. So when I put 12 it gives 4.52. It is bigger than this, so it's okay. Here on this corner of the shorter span we didn't have a moment, but we have to put a minimum reinforcement, so we put this one that we have here. So I like to put this to be phi of 8 spaced by 25 cm, so give us 2.01 of reinforcement there. And since it's for negative moment, will be on the top that we put another on the top on this side where we calculate this moment, 26 here. So on this corner, on the top, this reinforcement. The K, so the moment is what is changing here, and it's so this K will be minor than the 0.167 of the K limit to be single reinforced, of course. The lever arm calculated by this K will be 0.13331. So the reinforcement given by this expression will be 5.89. And here I didn't use the 25 spacing because if I put 25, I have 4. If you use the same steel, 12, 4, that is less. So using the 12, but shrinking the space for 25.65, still not enough for the steel that we calculated. So going to 15, spacing by 57.54. So this is why we calculate this, and we will end up using this. We'll use iron rods of 12 spaced by 15 cm. Okay, so it will be like this on the shorter side, the slab. On the bottom we have 12 spaced by 25. On the corners, negative moments on superior. On the top, this top will be 12 spaced by 15. On the other corner we'll have this minimum, phi of 8 spaced by 25, give us 2.01 Okay, for the shortest span, 5 meters. So going now to calculate the moments we got on the longer span, 7 meters, and support will be like this. There will be rigidity. So in the middle span we calculated 11.05. On this corner, the negative moment on the support will be 26.86. No. On this corner will be 14.61. We go here, it's M5 14.61. On the other side, 14.61. So 14.61 on the top. So we have here the moment on the bottom, 11.05. The K is given by that expression. So, and is limited by this, so we singly reinforce it. The lever arm will use this expression of the Eurocode that is limited by 0.95 multiplied by the effective depth. So we get this lever arm 0.133 in relation to this K that we calculated. And the reinforcement will be given by that expression, factor moment divided by 0.87 multiplied by Fyk multiplied by the lever arm Z. So, and we get this value. On the top, these negative moments, 14.61. So the K by that expression will give us 0.037. K limit is this, single reinforcement. Lever arm will be calculated by this K. Will give us 3.16 square meters per meter, square centimeters per meter. On the other side, the moment is the same, so the values will be the same. And main reinforcement the same here on the top. So here on the bottom we get this steel, and we have a 2.39. If we use 25 spaced by 25, it gives us 2.01. That is not enough what we calculate, so this is why I use it spaced by 20, 2.51. That is already complying with the main reinforcement. This main reinforcement is okay for the minimum that we calculated. So we use a diameter of 8 spaced by 20. On the top of the left is 1461. So the main reinforcement was 3.16. And using diameter of 10 spaced by 20 here on the top, gives 393. So I use the same spacing of 20. If we use 25, 340, it's not enough, so 20 spaced by 20 centimeters. And 10, if we use 8 to 51, it's not enough for the reinforcement, so this is why we use 10, the 393. Here on the reinforcement top on the other side is exactly the same, so it will be diameter of 10 spaced by 20 cm. So this longer span, 7 meters. Here on the bottom will be diameter of 8 spaced by 20 that we calculated. Here on the other corner, diameter of 10 spaced by 20. In the other corner is exactly the same value. So we have checked for flexure the moment we have calculated, and we need to check for the shear. So for the shear at the ultimate limit state, and we have on the British Code that table for shear 2. As we know, it's one major size continuous. So on the British, we go to the other table. This was for moment, and here we go down. Shear force coefficients. These coefficients, one long is continuous. So, and for 1.4, one long will be these coefficients, 0.49, 0.32, and here the other 0.36. So since this is the bigger coefficient, this is why we're going to check only for this one, 0.49. All this beta, this is the bigger one, so we check just for this one. And the expression to calculate this shear will be the VSV equal to beta multiplied by the factor load by the L, the minus 10. So it will be 0.49, that is the bigger one, multiplied by the 1579 that we calculated, the factor load at ultimate limit state, multiplied by the minus 10, that is 5, what gives us 3869 kilonewtons per meter. Okay, on the Eurocode we can see the K will be given by this expression, and the D will be in millimeters, and it has to be smaller or equal to 2. So if is not, well, then we adopt the value 2, and that's what happened here. To give us 2 for K. This K that we are after is because of this equation, that the shear that we calculated has to be minor than the VRD, and this VRD has to be bigger or equal to 0.035 K elevated by 3 divided by 2 multiplied by FCK plus this K1 multiplied by extension. Of course, here's this K1 and will be 0 the value, because we don't have actual force or per stressing. So here on the expression this will be 0 and here will be 0. We just need to get other values. This K will be equal to 2. The rho here that we calculated will be given by the steel divided by B multiplied by D, and has to be minor or equal to 0.02. And here this main reinforcement, I use half of this reinforcement to check the shear, because it's on the corners and we only need to put there 50% of the reinforcement that we calculated. If we check, for example, here, this in the main reinforcement in the bottom was 4.52, and on the corners this value will go here on the bottom, to one corner to the other, and we only need on the corners 50% of the reinforcement when we do the detailing of the reinforcement. So okay, so I use this divided by 2, of course I pass to the same units, divided by 1 meter, that is the B, multiplied by 0.14, that is the effective depth, what gives us this row, 0.0016, that is less than the 0.02 of the Eurocode. So it's okay. The CRD will be 0.18 divided by a safety factor This 1.5 what give us 0.12. So for the minimum shear we'll get it will be equal to 0.035, that is on this expression, multiplied by K, that is 2, multiplied by FCK of concrete, that is 20, divided by this, plus K1, that this is already all 0 because there is no actual force. All this multiplied by B, that is 1, multiplied by D, that is 0.14. So this gives us 61.98, the minimum shear. And for VRD gives us, on the other expression, gives us 49.67. So the maximum between these two for the resistance is this one, 61.98, and since what we calculated was 38.68 here, 38.68, it's less or equal, is minor than the resistance 61, so it checks for shear, so it doesn't require shear reinforcement. This is in the Eurocode at 6.2.2, members not requiring shear reinforcement. Okay. So we have this, we can go to the detail, the general detail of the reinforcement. Of this slab. This side is continuous, 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 continuous. Here's 5 meters, here's 7, it's 2-way single reinforced slab. So in the bottom, reinforcement will be this one. So let me increase this. Okay, so in the bottom what we calculated was this. Let's go to the shorter side. On the bottom we have at middle span 12, 15, 12 specified 25, so from this corner to the other corner 12 spaced by 25 on the shorter span, the bottom reinforcement. So and on the longer span, let's go see here on the bottom for reinforcement we have in the other direction, so it was the minimum that we not the minimum, but it gives us diameter of 8 spaced by 20, diameter of 8 spaced by 20. So this on the longer span there will be all this covering, this reinforcement will be all here covering these 5 meters. On the longer span it will grow here, it will go here, here, one corner to the other, and here, 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 spaced by 20. And okay, so this will be the reinforcement on the bottom of the slab. Now on the top, let me increase this better. On the top, the reinforcement, so if you go check on the top, in the shorter side, on the top we have this that we calculated for one side, 12 spaced by 15, and the other there was the minimum because the support there it because it's continuous. So 12 spaced by 15. Look into the shorter. So it's supposed to be 12 spaced by 15. And in the other, diameter of 8 spaced by 25. That's 25, it's correct. Okay. And this will be 1/3 of the length of this side. So it will cover from there, on this corner, from this corner to here will be 1/3, and 1/3 of 5 is 1.67. 1.67. 5 divided by 3 is 1.63. It will be the length of this reinforcement on the other side too, 1.67, and we will cover all the major sides. Okay, so now going to check on the, we have this there, and now the reinforcement, we have this one and this one on the top, and now the reinforcement for this one and this one on the longer span that we calculate. So here the longer span, on the top the reinforcement will be this one, diameter of 10 spaced by 20, and the other side the same. Diameter of 10 spaced by 20 cm, and the other side too, and this will be, this length of this reinforcement will be 1/3 of the longer span, 7. So 7 divided by 3 gives us 2.33. 2.33, and it will cover all this side, and here too this will cover all the 5 meters. It will be growing here, this diameter of 10 spaced by 20. Okay, so now it's missing the distribution bars on this, and the distribution bars we're gonna adopt. We have this minimum 2.01 square centimeters spaced by, so diameter of 8 spaced by 25 for minimum, and these distribution bars are usually 20%, 0.20 multiplied by the steel that was here on the bottom, 0.87. so this is why using this we will verify the minimum, and if we check there, so we will use this minimum for distribution bars, diameter of 8 spaced by 25 cm here on the detail of the iron rods. So we're gonna put here, and so here on the bottom was diameter of 20, 8 spaced by 20, so I just decided to use this minimum. Since it was on the bottom spaced by 20, I just decided to use the same diameter of 8 spaced by 20. It's more, so it gives 2.51 square centimeters per meter. So just to have the same spacing here, we'll have this distribution bars occupying 1/3 too. They will go so they will go this distribution bars here, diameter of 8 spaced by 20, 1/3, and here too on the shorter span, growing 1/3 spaced by 20 here, this side, on the other side too, distribution bars, and in the longer span we do the same, this and here distribution bars too, on the this side 2.33 and 2.33. It will multiply here these bars of 8 millimeters on 2.33. So this will be the detail of the reinforcement, and of course, as we know, for a more detail, we can attain more detailed reinforcement that we can divide this bar, for example, on two, one covering here on the center, diameter of 8, spaced by 14 cm, another going all the way, spaced by 14 cm, going to the corners, because on the corners here on the corners we just need 50%, and here too 50% to attach there, and on the other direction too 50% here on the corner and 15% here on the corner, so we can get more detail. If we wish, we can get more detail. This is what some softwares do. This diameter was of spaced by 25 on this direction, 25. So if we put the diameter spaced, we double the spacing 15, we can put one bar that is this one, and after that we put another bar that goes from the corners to the other corner spaced by 10, and we go on that one. So we are just putting 50% of the reinforcement here, and in the other direction the same. Here was a diameter of 8 spaced by 20, and multiply the space of 1, we'll have this here on the center, and will go all the way, because we only need 50% of the reinforcement here. Okay. For now, the general reinforcement will be this one. Now let's compare the results we got with the results of a commercial software. So we have here these results for the reinforcement. These ones are the results in the commercial software. So this is the shorter span, the 5 meters, and this is the longer span. So let's look to what the software gave us. In the shorter span, here on the bottom, it gave us a diameter of 12 spaced by 25. If we go compare, shorter span, 12 spaced by 25. So it was the same. Here on the tops, in the shorter side, he gave us diameter of 12 spaced by 20 one side, and in the other side, and he considered for this length 1/3 of 5, that is 1.67. When we look to our calculations, it's 167 in the shorter side, so it's exactly the same. And he considered diameter of 12 spaced by 20, but there is one thing that this commercial software considered, that is the combination of factors. So here on the top, he always put some bars here, all the way the minimum still. diameter of 8 spaced by 20, that in the calculations we have considered this minimum still. So we always put this. So this is going to affect this one on the corners, because now there is 2. So when we look to ours calculation, in the shorter side we have 12 spaced by 15 one side, and we consider in the other corner diameter of 8 spaced by 25. So look here, 12 spaced by 15. What happened in the program is, since you add this extra bar always to protect against other types of combinations that can be the wind or something, so we put this is affected here. It's 12 spaced by 20, and in our calculation was 12 spaced by 15, but he was able to increase this because it has added this on the top of 8 spaced by 20. So the result is the same, but what the software did, it was considered a combination of wind or other factors that can generate the traction here on the top fiber of the concrete. So we place this minimum reinforcement to be able to secure. Okay, so and here of 12, and in the other side the diameter of 8 spaced by 20. Okay, so till here everything is fine, and like we calculated, and even here is 1.67, 1.67, and so now going to the longer span, so the 7 meters, 1/3 of the span was 2.34 here in the program, and in our calculation was 1.33. It was really 134 in glued around, so it's exactly the same. On the bottom, so he gave us a diameter of 8 spaced by 20 on the bottom in the positive. If we go look what we calculated, we got a diameter of 8 spaced by 20. Let's see here, diameter on the bottom of 8 spaced by 20 here on the longer span. Okay, so it's exactly the same in the software, and on the software continues using the minimum still here on the minimum reinforcement on the half span. You always consider the combinations of many factors and wind. This is why you put the diameter of 8, 20 going one side to the other one. Otherwise it will be the same. Okay, this on the top reinforcement 2.34 length, and on this side was diameter of 10 spaced by 20. On the other side, diameter of 10 spaced by 20 centimeters. And what we calculated was exactly the same. Here for the top, diameter of 10 spaced by 20 on the longer span, diameter of 10 spaced by 20. Exactly the same. So the main difference is just the software considers the combination, and so it doesn't let you put all these minimums still here on the top fiber of the section. So our calculations are correct, and when compared with software is the same.